Hi, welcome back. This is part 3B, the second part of lesson 3, where we are going to make some significant improvements on the memory consumption, both of the flash program memory and of the static RAM that is being used by this sketch. I've already done a quick walkthrough in part 3A of the video, and what I'm going to do now is walk you through the changes that I've done in 3B. I've already loaded up the sketch here. Now I'm not going to show you what I've done inside here. If you've already loaded it from the blog post, fair enough, and have had a look at it, you'll see what the changes have been. But I'm just going to very quickly just simply compile this so you can see how much memory has been saved already. The 3A sketch was 8,434 bytes. We're now down to 7,810. So we've saved over 600 bytes of program space, and yet we haven't lost any functionality, and you'll see this as we go through. But what about the RAM? Right? Before, we only had 693 bytes of RAM left. So bring up this. Okay, here's our little thing. We'll just read an analog port again. Alright, so now we have 1,619 left. That is a significant improvement. I mean, that's almost a 1,000 bytes, which is 50% of what this chip even has in it. We've now recovered from the changes that I've made, and we haven't lost any functionality whatsoever. Now I could improve it even more than that, but I don't want to lose you guys off in doing any really fancy coding and things to get it as optimal as I could. So what I've done is what is reasonably optimal. Later on I might have to resort to doing even more tuning, depending on the libraries we end up loading and what memory we have left. But for now this will suffice. So 7810 bytes of program space used, and 1,619 bytes of RAM is still free. That means we're actually using less memory now than we were for the lesson 2 sketch. So we've improved this thing considerably. Alright, now let's now go into the code and see what we have done, and I'll talk through each piece as we've done it. Okay, so the first thing you'll have noticed, even though you may not know what it is we've included a new library. This is PGM space. What this library does, or the part we're using, is it allows us to define things to the compiler to keep them into the program space. Not so say a string, when you declare it as a string and then you run the program, one of the first things the compiler does is copy them into RAM. By using program space functionality, you can actually instruct the compiled code to not do that. Now the only downside is that the running program can't access those strings when they're not in RAM. So you have to make compensating code to copy them into RAM when you need them. But that's a small price to pay, because you write it once and you use it every time you want to play with a string. So what that does is it may slow your code down marginally when you're doing this, but it preserves a huge amount of the memory that you're going to be using. Alright, so how does this work? Well, you include the library, and I've defined a 128 byte buffer for program memory. Remember just before I said you have to copy it into RAM. So I've allowed 128 bytes for this. Now depending on how big the strings are that you define in the program space, you could reduce this even further. Alright, you could go down to maybe a 50 byte buffer or something, but you'd have to keep your strings smaller, which means a lot more calls to certain functionality. Alright, so I figured 128 bytes. As you saw, I've already saved a 1,000 or close to 1,000 bytes of RAM by just doing the things I've done in here, and that's even allowing for the fact that I've got this 128 byte buffer. Okay, so I could make it even better if I fine-tune the size of that buffer, but I'm not going to. This is good enough for now. So you already know the definitions for the pins. Not going to touch that one. Alright, so character input buffer, serial index, that's the same as before. So here's the first thing that's going to be a little different. Okay, and you're going to see this. One of the things I said that, and it was in the title of in the write-up for lesson 3, is that we're going to start using case statements for determining what commands are being used. Now, a case statement doesn't use strings. It can't. It uses basically byte characters for its decision, or an integer. So it can work with 1, 2, 3, 4, 5, or A, B, C, D, E. It cannot work with hello, goodbye, and things like that. So we have to have a way of converting our strings that we're looking for into an integer value that we can use for a case statement. So one of the ways of doing this is using an enumeration, and as I go through this, the picture will slowly become clearer to you. So I have the first enumeration I have here is for the text that I actually output to various responses of commands and things that come in. Right, so you'll see as we go through here, there's welcome text 0, and it says hello, please ask me something, blah blah blah. Now, because I kept the strings to less than 128, obviously I have to do certain strings over multiple declarations. So if you see, the 0, 1, 2 constitute that hello screen when you first connect the console. So there's welcome 0, welcome 1, welcome 2. If you know how an enumeration works, welcome text 0 will be given the value 0, then 1, then 2. Web text 0 will be given the value 3, 4, 5, 6, 7, 8, 9, 10, etc. So it all works very, very easily, and it just gives you a value from a friendly name. And I can actually, instead of referring to 0, 1, 2, 3, 4, 5 in my code later on, like a declare statement, I can actually refer to these by these names, which are much easier to read when you're going back to the code later on, and they're much easier to remember when you're actually even writing the code. Now, one of the other things that's really, really cool here is that I have this is numeric parameter and is not numeric param. These are two strings that I have down here, which are actually part of my debug output that I'm using. So if I turn debug off, do I really want my memory to be consumed by these two strings? No, I don't. So what you can do is you can put the if debug compiler statements before and after the pieces of code that you don't want to be included if you are not running the debug version. And you can even do this right in the middle of an enum declaration like this, or you can even do it in a bunch of other statements like here, where I've got an if debug. So there's the matching two strings for those last two enums that were shown above, that I've got an if debug end if around them. So if I turn off debugging, these will disappear from the end resulting code. Now, PROGMEM. This is the statement that becomes available when you start including this library, right? The one right here, the program space. And what happens here is this gives it's effectively like a little compiler macro that tells the compiler not to, and the runtime, not to put this text into RAM when it would normally try to do that. And you've got different declarations for your characters and ints and longs and everything else as well. So PROGMEM is the prefix, just like a constant and various other ones. Prog character is just declaring the fact that we have a character, and then it's welcome text 0, and we're saying an array here, and then we've got the string. So you use it. This is very much the same as saying constant character, welcome text bracket, where you would have it being loaded into RAM. Okay. So what I've done is every single string that I've been, or most of the longer ones that I've been using in the code, I've now represented here as a series of PROGMEM prog character and then the character arrays containing the strings. Right? All of these are going to be kept in the flash RAM. They will not be copied into the runtime RAM that's used with the stacks and everything else. Now, in order to access these easily, you need to put them into a set of pointer array. So what we have here is this is the text table array that contains, which is just pointers, which makes it much easier to handle this, because I just want to refer to these by a number, not by a name or anything else, and load them into memory. So by having this constant character pointer table, it gives me an easy way to index into these. Right, so I've got the starting position for every single string here. Now in this case it's just a PROGMEM constant character. I don't have to say prog character for this, and because they're just simple character pointers. Okay, and then again I've got this if debug for the two parameters that won't be there if I'm running in debug mode. So then the next part I have here is basically it's a repeat of what I've just described. So we have an enum, and this time it's for all the commands that we're using. So now the commands are effectively assigned a value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. But I can refer to them in code by these friendly names. And then I've got the text that represents all of the different commands listed down here. So I'm still going to be comparing to hello or goodbye or do something, web 1, 2, 3, 4, 5, analog, digital, PWMs. But I'm not going to be comparing them directly in the way that I was in the sketch of 3A. The same thing applies after the definition of all of the strings. I have a command table that has a pointer in order to every single one of the strings above. Now this enum, one of the things to note with the enum is it's 0, 1, 2, 3, 4, 5, blah blah blah, all the way up to PWM5. Alright, counting up. That you need to make sure that that is in the same order as all of these strings are, and then this pointer array, the command table, also needs to be in the exact same order. Now the nice thing about this now is that the value of one of these enums is exactly the right value to use as an index in this table to get at the command that I want to compare to. Okay, so just remember that in the back of your head. The other thing I've got here for the purpose of scanning through this table is I want to know how many commands I've got. I don't want to count them every single time I add extra commands to this. So this little function here, size of the command table, well this is the command table here, and then size of the command table 0, which we know is just a character pointer. So what it does is it takes the whole size of this table, divides it by the size of one pointer, and it gives me a count to tell me how many commands are in here. It's actually how many are in this one, but because this matches this, it works for all of them. Alright, so a quick little technique there for calculating the size of the quantity of entries in a particular table or array. So the next thing we got here is a function. Now this function is designed to return me a character array from program memory given the table name and the index into that table. Now here's where those enums come in handy when I end up calling this, and you'll see what will happen. So what happens inside here is we declare a buffer of the size PROGMEM buffer, which we declared up in the declare statements at the beginning of the program. And the first thing we do is we copy. Now this strict copy P is a special one for using the PROGMEM, and we copy it into the buffer from the table index pointed to from the parameters that we passed into it, and then we just simply return the character buffer. So you can see there's not a lot to be able to actually get into these arrays and return the strings from them. Right, the same for this one. It's the same function for both of these. All we do is refer to either txt table or we refer to command table, and away we go. The function itself here works for both of them. Now because we're using case statements for the searching and for the deciding which command we're actually going to be using and executing on, we need to have a method to find the command. So given, and you remember this when we went through 3A, we now take the first parameter and we assign it to a variable called command. So that command variable is a string. Alright, we need it to be an integer so that we can use it with the case statement to keep that thing a lot simpler. So we have to iterate through this list of commands, and we have to find the one that matches, and that's going to give us an index value that we can then use for the case statement later on. So this find command does exactly that. Alright, here's our search text, which is basically the command that was found when we analyzed the input string from the serial port. We start from 0 and we go to the found index is basically just acting as like a Boolean flag to say that we have not or have found the command. So we just do a loop, and we just basically are going to loop through the array of commands above, and we're going to compare them. Now you can see here we're using the exact same command for comparing. It's still strcomp that we used in 3a and lesson 2. The search text is exactly the same as we used in 2 and 3a. What's changed here is we're now calling this function, which is getString from PROGMEM, which I just described before, where you give it a table name and you give it an index into that table. That returns a character pointer, which is exactly what strcomp needs for its second parameter. So what we're really saying is if strcomp, the command that came in the serial port, matches the command in the table, then return the index of that command. Alright, and the minute we find it, which is based on the strcomp, the found index equals the index, so that'll be 0, 1, 2, 3, 4, 5 up to the maximum number of commands, and we just break out of the while loop. If we don't find it on the first one through, we increment the counter and we try the next and next and next until we end up at the end. Alright, now obviously if we don't find the command, we're going to return a -1. Alright, so that's what find command does. Very straightforward, very easy. Setup is exactly the same as it was before, with the exception of outputting the pretty instructions. Now it's 3 print statements. There is no text here at all now, and what we're doing is we're saying print getString from program memory, which returns the buffer into that 128-byte buffer, and then the print statement just takes it and sends it out the serial port. So again, we're just copying things down from the program memory into one particular buffer of RAM, and we're using that for pretty much everything that we need. Alright, so much simpler. The loop doesn't change. Again, it's exactly as it was before. Now do command, first part is exactly the same, and even the command strtalk and the parameter strtalk, where we pass the line out and we get the 2 different parts of the line that are delimited by one of the predefined delimiters, is exactly the same. Alright, even down here, the out parameter and setting the analog value, that's exactly the same. So where the things change, okay, here is where we had that massive, great big if then, else if, etc., all the way down for all the commands. Alright, this has now been replaced by a call to the find command with the command string, which we used to use for the strcomps all the way down here, and that returns an integer index into this into this case statement, which is used as the command ID. And then now we can just simply say switch command ID, which is the 0 through whichever one it finds, and then case hello. Now here's the use of the enums, right? This is just basically saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. But if I had used 0, 1, 2, 3, 4, 5, and then I inserted some extra ones or something like that, you know, maybe I put a whole bunch of some other kind of temperature sensor things in the middle here, that would screw up all of my indexing, and I would have to rename everything else, and it'd be a real pain in the butt. But I could just extend that enum statement quite easily and then just put the friendly text in here and not have to change anything else, and it would work just fine. Now the other part here is that's happening is it's a case, so it's very quick, very simple, and then I'm still, you know, the first one, hello, goodbye, do something. Before they had a whole bunch of serial outputs. Now what I'm doing here is hello just does the getString from prog memory again, alright, and then breaks out of the thing. Same for goodbye, same for do something. Where 1, 2, 3, 4, and 5 has a function called the process web command, and it gives it a very short string. So this is the unique piece of those different web statements. Alright, now if I quickly go down to the process web command, it's a new function I added in here. Where'd I put it? Oh, very end. Alright, all it is it takes that web text in as a parameter, and then it just does the serial print get from prog memory. So these you've already now aware of how they work, and then it prints the first two, which is basically the header information and the start of the body tags, and then it outputs the actual unique text, and then it finishes off with the closing body tags and closing off the HTML. So now this one function here replaces 5 separate sets of code and only deals with the unique aspect of it. Now, obviously, in a later lab, we're going to even get rid of this, and all of that text for the web we're actually going to end up putting in an SD card, which will reduce the footprint even further. But for now, for this simple example, you can see how we've taken 5 separate commands, which were probably as long as this, and we've replaced them with just a single function with only the unique aspect being called out as a parameter. Alright, so let's get back up to the code. So that was the webs, and then analog 0, 1, 2, 3, 4, 5. As you can see here, now instead of having the code for every single analog dealing with the unique port, we're calling get analog, and we're giving it the unique parameter using the pin number. All right. Now the get analog is also down the bottom here. All right, right here. So what this is doing is the same as the 3A code, only it's been wrapped up into a function, and the unique aspect of each of those separate ones that were in 3A have now been put into a single statement here. Okay. So it's printing the analog value that you send in. It's printing out the digital value that it read from the serial port, and then it's printing out the adjusted value to give you the volts from 0 to 5 volts. Okay. While we're here, let's just look at get digital. This is another example where we've taken repeated code and we've made a function call out of it because it gets reused, and now we can use this for all sorts of things. All right. Now I've modified this one slightly by having it prints the current value of the digital port. Alright, so it reads it and it prints it out, or whatever it is, and then if the value is -1, so that's that check we had up above, then we're going, if the value I input on the serial port is a -1, then I'm going to output pin 1 and invert it, right? Rephrase that. If the value is -1, I'm going to flip the output of the pin, which is basically what the previous code did on 3A, only that was the only kind of functionality and didn't care if it was -1. It was, if there was any second parameter, it would just flip-flop the bit. Alright, this one now you specifically have to say if -1, flip the bit. Otherwise, if the value is 0, output a low. If the value is a 1, output a high. Any other value, then print an invalid value error message. Alright, so this is now a little more refined, so we've actually got more functionality here than what we had before, and yet we're still using less program space. And it works very, very easily and very simply. Again, the messages are all coming from the program memory space, so we're not having to have any strings being pushed into the RAM space unnecessarily. And then the last part we got here is the process web command, which we've already talked about. So if I go back to our functionality here now, alright, here's the digitals, and you can see the digitals taking 2 parameters into it. We've got the pin number, D0 through D7, and then we have the value that we want to output. Now we're ignoring in the PWM functionality here, you'll see where things behave a little differently. Oh, I think if I remember what I changed correctly. Alright, let's go look at the PWM. Alright, so we're taking the pin number and the value. So if the PWM will print what we had come in, and then we analog write the value to the PWM. Alright, but if you look at the I think I haven't included the code based on the PWM range in here. So what I'll do is, so this bit here, the out parameter is currently being ignored. on the PWM. That's fine. Just remember that it's not being used at the moment. You can actually add that extra check in if you want to limit the PWM range. Anyway, so all you would have to do here if you were using the value check from up here is this out parameter. You can try that as a piece of homework if you like. On the PWM, right, you've got the pin and the value. So you could have a check in here that says if out parameter equals equals true, then allow this to happen, else write an error message. Alright, that's all you would have to do for this one. So what I'll do is I'll make sure that that check is included in the posted code when I put this up on the blog. So by the time you're actually seeing this, those changes should be in there. So PWMs, and then the last thing, of course, is these are all got numbers, not 1, 2, 3, 4, 5, all the way up to the enum assignment for PWM5. If it doesn't find a match in all of these, this default statement here actually catches anything that's not already been caught with the case statements. So if it gets to here, then it's going to output the command buffer and the fact that it couldn't find the command. So it's the error text, and whatever you sent in as the command buffer is also going to get output. And then at the very end, we've got the same thing from lesson 2 and lesson 3a for the debug parameters, and output the parameter if there is one, output the free RAM. Okay. So nuts and bolts of it is the case statement shaves a huge amount of program space out of the code. So that's probably one of the few areas that's been responsible for saving a lot of the program flash memory space. Making these modules, these functions, and calling them saves program space, because now you're not duplicating common code again and again and again. Okay, and then when it comes to the RAM, right, the working area for the stacks and buffers and everything else, by having these program memory declarations and a simple function to read the string into a buffer, which is effectively like a working buffer, and doing your comparisons one at a time against that, whilst it will slow down your program a small amount, you will save big time on how much memory you have used, and therefore allow yourself to put a lot more code in. Now the trick to all of this, of course, is you don't read your serial ports again and again and again in quick succession. You really don't need to. And one of the later lessons we're going to be reading a serial port, we're going to be reading from an Ethernet port, and maybe even some other input devices in a loop, and we're going to use the same buffer, the same command processing and everything else for all of them. So again, we're going to enhance the reuse of all of this. We're going to be using an SD card for outputting data as if it was a website out of an Ethernet port. Okay, instead of having these predefined strings in flash memory, which means it's going to recover a lot more of the flash space as well for that. But of course, while you're reading from the SD card, you can't be checking serial ports and everything else, because at the end of the day, it's just a single processor and it's busy doing its thing. Interrupts will be happening, of course, and they will be executing, but it's critical that you keep anything you put into an interrupt to a really, really short time. Okay, so you do the actions that you have to do, but you don't do any complicated math or processing. You save that for the areas of the code where it's not critical. Anyway, we will get into that later on a later lesson, but for now, I think what I've shown you here is that for a very small, well, relatively small, I mean, if you write it this way right from the bat, it really doesn't take you too much more time to do. It took me a little longer because, of course, I had to write all the code the way that I wouldn't normally write it first, which is like more of a beginner's style. And whilst in these examples both will work because we didn't run out of memory and we didn't run out of RAM, you can see how quickly it starts getting chewed up, and the minute we start adding other libraries, you would be running out. So it's a good habit to get into writing it and using PROGMEM space like this if you feel that you're going to get close to running out of your resources. So anyway, if you have questions, please post comments, post feedback. Give me a thumbs up if you like this, and I look forward to presenting lesson 4 very, very soon. Okay, thanks. Bye.